Okay, can I have everyone's attention, please? So let's go ahead and start. I wanted to remind you that your midterm scores are already posted on the class website. As we speak, your exams are being scanned, and within a few days you will receive a PDF file of your graded exam. All right? So if you have any questions about the grading, you should wait until you receive a PDF file of your scanned exam and then take a look at it. But in the meantime, it is important that you go to discussion this week, because during discussion this week, we will actually go through the answers from the exam. And I want to remind you guys that this is important because this is the first midterm, and I want to make sure that you get feedback on your performance on the exam. So the TAs are going to point out to you mistakes that students made. We graded fairly strictly, so most of the questions were either right or wrong, so you have to get the entire question correctly. All right? I must confess that the class did really well. I am really pleased. All right, the scores were good. The exam was not an easy test, and so overall the class did very well, and I think kudos for you guys. But remember, the battle is not over. This is just the first hump. So now we need to get through the whole quarter, so I want you to keep that momentum. All right? And so please go to discussion this week. The TAs will go through the answer key with you, and if you have any questions, they'll answer those questions. They're the ones who graded the exam, and they'll tell you how the exam was graded as well. And this is important because I want you to have that information as you prepare for the second midterm, because that's how your exams will be graded on the second midterm as well. Okay? Now, before I proceed, does anybody have any questions? Great. So if you guys remember, we're just going to pick up where we stopped. And last time we talked about acid-base titrations. And the timing is pretty good because I understand you're doing that in the lab right now. Okay? So if you take titrations in general, titrations, we said, are an analytical tool. It's a tool used to analyze or determine the concentration of an unknown substance or element in a solution. All right? So if we want to determine the concentration or amount of a substance in a solution, we have to take advantage of a reaction. All right? And titrations take advantage of a reaction that has to be very clean, no side reactions. That's the only reaction taking place. So it has to be a reaction that's clean. It has to be quantitative, which means that it has to react completely. And thirdly, it has to be rapid. You can't sit there for days waiting for the reaction to go to completion. So we take advantage of reactions that are clean, quantitative, and rapid. All right? And so it turns out acid-base reactions are ideal for this, because acid-base reactions react rapidly, cleanly, and quantitatively. Okay? So when you are looking at titrations, we look at a reaction where one of the reactants, you know what the concentration is. All right? And the solution with the known concentration, the reactant with the known concentration, is always placed in the burette. And that is called the titrant. We place the solution of the unknown concentration in the Erlenmeyer flask, and we call that the analyte. And then what you do is you carefully measure amounts of the titrant into the analyte. So carefully, that's why we use the burette, to carefully measure volumes of the titrant into the analyte, and you mix it up really well so that the reaction goes to completion. All right? At some point, as you add titrant incrementally, there's going to come a point where the reaction goes to completion. And when the reaction goes to completion, it's signaled by some change in physical property. So it turns out you can use many different physical properties to signal where the titration goes to completion. Now, the most common way to do that is to add another reagent, which we call an indicator. And in the laboratory, you would have carried out an acid-base titration where you added phenolphthalein as the indicator. And so if your analyte is an acid, when you add the phenolphthalein indicator, it's colorless. And then you add the base. As you keep adding the base, there comes a point in which the acid and the base would have reacted completely, so that now at some point you're going to have a slight excess of base. So if you're adding the base in increments, there's going to come to a point where you're going to have a slight excess of base over the acid. All right? At that point, your indicator turns pink. All right? Because phenolphthalein is colorless when the solution is acidic, but it turns pink when the solution is basic. So when all the acid has been used up in the reaction, and now all you have is just a little bit of excess base in there, then the solution turns pink, and that indicates that the reaction is completed. Okay? So that's if you use an indicator. Another way, or another physical property that you can use to signal the completion of the reaction is to look at the pH. Remember, if you have an acid, we're looking at acid-base titrations, and if you place the acid as in the flask and you put a pH meter in there. pH meters, you guys have used pH meters, isn't it? It has electrode, you put the electrode in the solution, and then the meter reads out what the pH of that solution is. And if you have an acid in there, what should the pH read? Less than 7, 7, greater than 7. Less than 7. So to begin with, you have only acid there, and you're going to read a really low pH. Now, as you add the base, what's going to happen is that the base will react with the acid, and so the acid is consumed. So the pH will go up. All right? And so what we look at is the change in pH. So incrementally, you add the base to the acid, and in the pH meter, you read the pH. And then you can plot out what we call a titration curve. All right? And we said a titration curve is a plot. So if you look at a titration curve is a plot of the pH of the analyte. All right, so this is what is in the flask as a function of the volume of titrant, which is in the burette, added. All right, so if you make a plot of the pH as a function of volume of titrant added, usually this is in milliliters. All right, if you make a plot of this, we call this plot a titration curve. All right? So instead of what you did in the laboratory, I think you're doing both in the laboratory, where you're going to look at phenolphthalein using an indicator. That's one way of carrying out a titration, where the physical property that you're looking at is adding a third reagent, which we call an indicator. Or the other way is to measure, put a pH meter in there and measure the change in pH as you add the titrant. Is that clear to everybody? So it turns out that acid-base titrations can be of 3 types. So we're going to look at acid-base titrations in detail. And the reason we're looking at acid-base titrations is because we're going to apply everything that we've learned up to this point. Remember, we looked at the fact that you now know how to calculate the pH of a weak acid. You know how to calculate the pH of a strong acid. You know how to calculate the pH of a weak base. You know how to calculate the pH of a strong base. You know how to calculate the pH of a buffer. All right? So this is one place we're going to apply everything that we've learned, and we're going to mix them together. We're going to look at how things change as you progress. All right? And so this is a very useful application of all the concepts that we've learned. Okay? So it turns out that acid-base titrations can be of 3 types. And the first is strong acid versus strong base. The second is weak acid versus strong base. The third is weak base versus strong acid. So it turns out they can be of three types depending on what is the titrant and what is the analyte. You can have both being strong. So you can have titrations with strong acid, strong base. All right? One of them will be the analyte, the other would be the titrant. Okay? Or you can have weak acid versus strong base. In this case, the weak acid is the analyte and the strong base is the titrant. Or the reverse, where the weak base is the analyte and the strong acid is the titrant. Okay? Now we never look at titrations between weak acids and weak bases because you can't get any meaningful information out of it. So you can't do titrations with weak acids, both being weak. All right? So either they have to both be strong, or one is weak and the other strong. Okay? So we're going to take a look at each one of these, and we're going to start by looking at the first of these, which is a strong acid versus strong base. And instead of using the phenolphthalein as the indicator, we're going to look at pH titration curves. All right? So we want to look at titration curves, and we want to look at the dependence of pH, because that's what we've been calculating all along as the volume of titrant has been added. Okay? So you can see that if I wanted a strong base, the classic strong acid strong base would be HCl aqueous versus NaOH. All right, and let's say to begin with, we will start with an example where our titrant is going to be the base. Okay, so we're going to start with 0.1 molar NaOH. So remember, that is the known concentration. Okay, in the flask, we're going to put HCl aqueous. So what we have here is a strong base as the titrant and a strong acid as the analyte. Okay, so as all of you know, we have a strong acid and strong base, and if we combine them, all of you recognize, remember, large amounts, strong acids produces hydronium ion. Strong bases like sodium hydroxide produces hydroxide. And we know that large amounts of hydronium ion and hydroxide ion can't coexist. What do? They're going to neutralize each other, and what do they form? Water. Okay? They can coexist in small amounts. Like in water, it's about 10 to the negative 7 molar. So hydronium ion and hydroxide can coexist only in very, very small amounts, all right, of the order of 10 to the negative 7. Otherwise, if you have large amounts of them, they're going to react with each other, neutralize each other, and form water. So let's look at what the reaction would be. All of you recognize that if we want to look at, we start by looking at what we call the net ionic equations. So we're going to look at all the major species that we start with at the beginning, and then look at the major species after the titration has occurred, okay, after you've added the analyte. So we have a strong acid. All of you know, what do we know about strong acids? Strong acids do what? Dissociate completely to give you hydronium ion and chloride ion. So we know that the initial HCl that we started with will give me H3O plus concentration, and that should be the initial Cl minus concentration as well. And we know that the initial concentration of sodium hydroxide, because it's a strong base and it dissociates completely, should give me the initial concentration of hydroxide, and because we have the same amounts of sodium and hydroxide, they should all be the same. Okay? So to begin with, I have H3O plus aqueous plus Cl minus aqueous. This is what's in the flask. It's a strong acid, dissociated completely, so these are the species in the flask. Now if I add sodium hydroxide to that, I have sodium hydroxide that is dissociated. So before any reaction starts, the instant I combine them, I'm going to have all 4 species in there. Does everybody recognize that? All right? But we know that because it's a strong acid, we have lots of this, and it's a strong base, we have lots of that, and they cannot coexist. So the instant we combine them, these two are going to react cleanly, rapidly, and quantitatively to give me what? H2O, and then I have sodium and chloride. If you see, NaCl is a salt, and once again, it's a soluble salt, and we know salts dissociate completely. So what I would have is, if you want to look at this, this is not the net ionic equation, I'm sorry. This is the complete ionic equation. So if you look at the complete ionic equation, this is what I have. These are the species to begin with. At the end of the reaction, this is what I would have. Now, if you look at these, you can see that really sodium is there at the beginning, it's there at the end. Chloride is there at the beginning, chloride is there at the end. So can everybody see that sodium and chloride are not doing anything at all? They're just hanging around. All right, they're there at the beginning, they're there at the end, they're not undergoing any change at all. And so we call them, these are called spectator ions. You can see that they're there at the beginning, they're there at the end, and therefore they're ions that don't do anything at all. So they're just spectators, not participating in the actual events that are taking place, and so we call them spectator ions. All right? Now, if I cancel out the spectator ions, because remember the spectator ions are there at the beginning, they're there at the end, what I end up with is what I call the net ionic equation. And so what we have is over here, the net ionic equation. And in the net ionic equation, we cancel out the spectator ions, because really spectator ions don't participate in the reaction. All right? So if I take the net ionic equation, that describes or summarizes exactly what's going on in this reaction. And so in acid-base reactions, essentially what happens is the acid and the base react with each other to give you water. All right? Now, if you want to write the general form of the equation, the general form of the equation is sometimes very misleading. So general reaction would be, we started with HCl plus NaOH giving you H2O plus NaCl. So often you would see the general form of the reaction where you write down the two reactants and the products that are formed. And you can see in the general form of the reaction, it doesn't really convey what's going on, because you know that HCl is a strong acid, it dissociates completely. NaOH is a strong base, it dissociates completely. They're going to give you water. And then we know that the salt that's produced, which is NaCl, is dissociated as well. Okay, so it just gives you the general form, but it does not give you the details of what's going on. But it's worthy to remember that in acid, when you combine an acid and a base, you always end up with water and salt. All right? And that's what that reaction kind of summarizes, that when you take this acid and this base and combine them, you're going to get water and then salt being formed. Okay? So now what we're going to do is we're going to apply what we learned. So we know that the bottom line is that the reaction that really takes place is really the hydronium ion from the strong acid and the hydroxide from the strong base combining to give you water. Okay? So that's what we're going to look at. So now we're going to go back and we're going to look at an example. And the example that we're going to look at is, we're going to start with 0.1 molar NaOH. All right? And over here, we're going to have HCl. But usually in a titration, remember the analyte concentration is unknown. All right? But because as a practice and as a mental exercise, what we're going to do is, usually in an experiment, your analyte is unknown and what you measure is pH. What we're going to do is we're going to calculate what the pH would be. All right, and we're going to calculate the pH of that solution. Then we need to know the concentration of the analyte as well. So what we have here is 100 milliliters of 0.1 molar HCl. So usually in an acid-base titration, you do not know what the concentration of the analyte is. That's what you're trying to figure out. But here what we're going to do is we're going to try to figure out what the pH of that solution is. But before we do that, I want to kind of show you the process. And so let's briefly just look at what you have done in the laboratory. All right? So
a titration is a controlled acid-base neutralization reaction. 20 milliliters of hydrochloric acid of an unknown molarity is added to a flask. 2 drops of indicator dye are added to the acidic solution. This indicator dye is clear in acidic solution and pink in basic solution. The burette is filled with a sodium hydroxide solution of known strength, and an initial reading is taken. The base is added to the acidic solution until the solution stays a slightly pink color. At this endpoint, a final reading is taken. The moles of base added equal the moles of acid present. This same reaction can be followed using a pH meter instead of an indicator dye. Initially, the pH changes very little as base is added. Suddenly, the pH changes rapidly as the endpoint passes. The solution quickly becomes very basic, and again, the pH changes very little. The endpoint occurs at this middle point on the curve.
So the end result is that I wanted to show you that curve. So in the laboratory, when you'd carry out that experiment, what you had was an unknown solution of the acid. You had the pH electrode placed inside the solution, and you measured the pH. And so what you did was you made a plot of the pH that you measured as you added, let's say, 5 milliliter increments of the base to the acid, and then you plotted pH versus the volume of titrant added. And the end result is that you would end up with a titration curve, and the titration curve looks something like this. So here is the titration curve for when you have an acid in the flask and your titrant is a base. Okay? So let's look at this point here. This point here is before you added any base. So you would expect all you have in the flask is just a strong acid, and therefore you would expect a very low pH. All right? And you can see that that pH is somewhere around 1. Okay? Now as you incrementally add base, and if your titration is a strong acid versus a strong base, then the shape of this curve comes out to be this S-shaped curve. We call that a sigmoidal curve. All right? And you will see that initially your flask is going to have acid, so your pH is going to be very, very low because the solution is acidic. But as you approach the end of the titration, where the two reactants are reacting in stoichiometric amounts or in similar amounts, then what happens is suddenly the pH changes dramatically, and suddenly you see this steep rise in pH. All right? And then once you've passed the equivalence point, now it slopes out. So when the two reagents, the strong acid and the strong base, have reacted completely with each other, we call that the equivalence point or the stoichiometric point. All right? The equivalence point is when they have both reacted in equivalent amounts. We call that the equivalence point. Now, sometimes in the laboratory, you've used the word endpoint. All right? Now, it's important to know that the endpoint and the equivalence point actually convey different information. The endpoint refers to when your indicator, if you're using an indicator, the endpoint refers to when the indicator changes color. All right? And an equivalence point refers to when they have reacted in equivalent points. So in some experiments, the equivalence point and the endpoint will be the same. In others, they will be different. All right, now let's take the phenolphthalein example. Remember, phenolphthalein changes color not when they have reacted completely with each other. Phenolphthalein changes color when you have a slight excess of the base. Because remember, when you add the base, phenolphthalein is colorless if it's acidic, it's colorless if it's neutral, but it only changes color if it's basic. Do you see that? And so when you add phenolphthalein as the indicator, the endpoint is actually when you have added a very slight excess of the base. That's why when you did the experiment, remember, you add sodium hydroxide, you stir it. So you add it in increments. And as you approach the end point, you actually had half a drop. How do you add a half a drop? Did you guys learn that in the laboratory? You kind of let a drop hang just halfway there. Then you take the lip of your flask and kind of get that half drop in there, and then you stir it. All right? And so when you approach the end point, you actually don't even add drops. Now you add half drops, so that there comes a point in which you see the first trace of the slightest pink. That means that's the end point. So the half drop that you added has to be subtracted, because remember, it turns pink only when you've added a slight excess. So that's why you do it in half drops, and a half drop is about 0.05 milliliters. All right? So you let a pendant drop hang on the tip of the burette, just a half a drop, and then you take the flask, the edge of the flask, and just touch it, and then you take it off and you tilt it and you mix that half a drop of base that you added. And so at that point, you're going to see the first trace of a pale pink. If it gets to be dark pink, you've gone way past the end point. All right? No help there. All right? You have to see the first trace of a permanent pink, because initially as the drop falls in, the solution will turn pink, and then when you stir it, it'll go away. All right? And so the first time you see the faintest of the faintest pink, that's when the end point is. And then if you really want to know what the equivalence point was, you take the end point and you subtract the half a drop that you added when it turned slight pink. And that will be the equivalence point. So that's why it's important that you realize the term endpoint refers to when you're using an indicator and the point at which the indicator changes color. Very often, when the indicator changes color is not the same as the equivalence point. The equivalence point, or the stoichiometric point, is when the two reagents have reacted in exact amounts. All right? So let's take a look at this. So at the equivalence point here, now we know that this is the reaction that's taking place. We know that when you have a strong acid and a strong base reacting, at the equivalence point, all of this has reacted completely with that. So at the equivalence point, what do I have in solution? Can you tell me? Initially, to begin with, you have lots of acid. You're slowly adding base. At the equivalence point, now you've added exactly the right amount for all the acid and all the base to neutralize each other. So at the equivalence point, what would you have in solution? Water and salt, sodium and chloride. Water is neutral. Na plus is a group 1 metal, neutral. Cl minus is what? The conjugate base of a strong acid. Conjugate base of a strong acid is a what? Neutral, basic, acidic. Neutral. So what should the pH be at the equivalence point? 7. So you know that if you're titrating a strong acid with a strong base, you know that the equivalence point has to be when the pH is 7. So all you have to do is plot this graph and then figure out what pH 7 is and figure out what the volume is, and that would be the volume of base that you added when all of the strong acid was completely neutralized by the strong base, and that would be the equivalence point, all right, or stoichiometric point. So one important take-home message is that you need to know what equivalence point is or stoichiometric point is, and you need to know what end point is, and they're different, okay? Okay, so now that we know what the plot should look like, we're going to start calculating this, all right? And because now we're not doing an experiment anymore, now we're doing theory, we're going to predetermine what the concentration of the acid is, we're going to predetermine what the concentration of the base is, and we're going to calculate the pH. Usually we measure the pH, all right? And we don't know what the concentration of the analyte is. That's what the experiment is. But now in class, what we're going to do is we know the concentration of the analyte, we know the concentration of the titrant. We're going to calculate what the pH of that solution should be. Okay? So to begin with, I'm going to have you help me out. So we're going to look at several scenarios. We're going to look at how do I calculate the pH before I add any base? How do I calculate the pH after I've added some base? How do I calculate the pH when we're at the equivalence point? And how do I calculate the pH when I have exceeded the equivalence point and I have lots of excess base? Is that clear to everybody? So let's start with the first, which is pH before addition of a base. So let's see, if I were to take a 0.1 molar HCl and put a pH electrode in there and I measure the pH, I should be able to calculate the pH that my pH meter should read. All right? So all we have in here is a strong acid. What is the pH of that solution? 1 minute. What is the pH of that HCl solution? Do you know? What is the pH of that solution?
1.
How many say it's 1? It's got to be 1. Why? It's 0.1 molar, 10 to the negative 1. Got it? It's a strong acid. Strong acids dissociate completely. And so by now, I need you guys to know this. Otherwise, I have to send you back to Chem 1B. All right? Because we've done many problems. You know that it's a strong acid. And so what I have is that we have the initial concentration of HCl is 0.1 molar. And we know that equals the initial concentration of the hydronium ion, because we know a strong acid dissociates completely. And remember, that means that is 1 times 10 to the negative 1 molar. 0.1 is 1 times 10 to the negative 1. Therefore, pH should be 1. And it goes to 3 decimals because our concentration is given to 3 significant figures. All right? So to begin with, we know the pH of the solution in the flask. All right? Now we're going to calculate the pH of the solution if I added 30 milliliters of NaOH. So the second case is pH after 30 milliliters of 0.1 molar NaOH. Remember, this is the titrant, is added. Okay? So what we have to keep in mind is, now if I wanted to figure out the pH of the analyte, because we're measuring the pH of the HCl after you added 30 milliliters of HCl, you want to keep in mind that in titrations, because we're adding base all the time to the analyte, can you see that the volume keeps changing? All right? If the volume changes, what does that tell us about concentration? What is the definition of concentration? Moles divided by volume. So if the volume keeps changing, what is that telling me about the concentration? It's going to keep changing all the time. All right? And because the volume is going to keep changing all the time, what we want to keep in mind is that what doesn't change is the moles of acid and the moles of base. Do you understand that? So what we're going to have to do is actually, instead of looking at it in terms of concentration, up to this point, every example of the problem that we dealt with when we looked at weak acids and calculated the pH, when we looked at weak bases and calculated the pH, when we looked at strong acids, strong bases, and even when we looked at buffers, one of the assumptions that we made was the volume never changed. So if the volume doesn't change, we know the concentration does not, we can keep the concentrations and we can calculate them based on the concentrations because they're not changing altogether. You understand that? Here, because we keep adding more and more base in our flask, the volume of the flask is continuously changing. And if it's continuously changing, the concentration is continuously changing as well. So what we need to do is actually calculate the moles rather than the concentration. Okay? So what we're going to do is we're going to calculate the moles of acid. So remember, the way to remember this is what I taught you last quarter. Remember, concentration or molarity is always moles times volume. That's all you need to remember. So if I need to calculate moles, what does that equal? Concentration times volume. And remember, concentration is always moles per liter. What is the unit for volume? Liters. So I have to make sure always that my volume is in liters. Okay? So if I want to calculate the initial moles, so I want to calculate the initial moles of hydronium ion. Remember, what is the universal symbol for moles? It's a lowercase n. All right? So if I'm calculating hydronium ion concentration, HCl is a strong acid. It dissociates completely. So whether I calculate the concentration of HCl or whether I calculate the concentration of hydronium ion, they're the same thing. All right? So if I want to calculate the moles of hydronium ion, this is going to be concentration times volume. The concentration we know in the flask is 0.1 moles per liter. And we said we have 100 milliliters of that solution. All right? So to begin with, the volume would be 0.100 liters, 100 milliliters. All right? And therefore, this comes out to be, it's in 3 significant figures, comes out to be 3 times 10 to the negative 2 moles of hydronium ion. So this is what I started with. This is the amount or the number of moles of HCl that's there to begin with. Okay? Now, if I want to calculate my initial number of moles of hydroxide, how much hydroxide did I add? 30 milliliters. Okay? So I have, once again, it's concentration times volume. So I know that I have 0.10 moles per liter. That's the concentration of my titrant. I added 30 milliliters. 30 milliliters makes 0.03 liters. And you can see liters and liters will cancel out. And this gives me 3 times 10 to the negative 3 moles of hydroxide. Is that clear to everybody? So what we've calculated is before any reaction took place, we've calculated the amount of hydronium I had and the amount of hydroxide that I had. Now remember, this is an acid-base reaction between a strong acid and a strong base, and we know that the net equation is where the hydronium reacts with hydroxide to give me liquid water. So before any reaction took place, I just calculated that I have 1 times 10 to the negative 2 moles of hydronium, and I have 3 times 10 to the negative 3 moles of hydroxide. Is that clear to everybody? So this is what I start with. Before any reaction took place, I've calculated the moles in the flask, and I've calculated the moles of the 30 milliliters of base that I added to the flask. Okay? So now they're going to react with each other. So after reaction, so can you see this is a stoichiometric problem? All right? And that means it's a limiting reagent problem. So which is limiting, which is excess? Can everybody see that hydroxide is limiting? It's in lesser amount. All right? So that means if it's limiting, when the reaction's complete, I'm going to end up with 0 of that. And so if I subtract this from this, I will have 7 times 10 to the negative 3 moles, where this is limiting and this is excess. We're not really concerned. We're just forming water, and we know water does not affect the pH. All right? And it's in excess amount, it's the solvent. So we're really not concerned about how much water is being produced. We're really just interested in how much acid and base are left over. All the base is consumed because it's limiting. And so what we're left over with is the excess acid. So when you add 30 milliliters of water into that solution, all the base is consumed, and all we're left with is hydronium ion. So now I need to figure out what is the hydronium ion concentration, because if I want to calculate pH, remember, ultimate goal is to calculate the pH. So if I want to calculate the hydronium ion concentration, so I'm going to say hydronium ion concentration, and this is the excess that's left over from this. All right? And what is the definition of concentration? It's always moles divided by volume. We just calculated the moles, which is 7 times 10 to the negative 3 moles. Now, what is the volume? Remember, the reason that we're calculating all of these in terms of moles is because the volume keeps changing. I started with 100 milliliters. I had 30 milliliters of base, so at that point, what is my volume now? 130. Can you see that? So what I have is I'm going to divide by the volume, which is 130 milliliters, or 0.130 liters. All right? So now that works out to 0.0538 molar. So I want you to keep in mind, in these problems, lots of things are going on. There is acid, there's base, we're having a reaction going on, neutralization taking place, and then we are left with what's left over. And you guys can handle problems of this type now because we've done so many complicated problems. Now you have to be able to bring all these multiple ideas together and kind of solve this problem. And you can do it because you already have all the tools to do it. Okay? So now that will be the hydronium ion concentration of that solution. How do I calculate pH? Take the negative log of that. And if you take the negative log of that, the pH of this solution comes out to be 1.269. So to begin with, the pH was 1. We added the strong base, 30 milliliters. Now you can see the pH went up because some of the hydronium ion has been consumed. So you have less hydronium ion in solution, pH goes up. Okay? So it turns out that you can calculate in this plot, we calculated, we figured out what the pH is to begin with. So we figured out this point. We added 30 milliliters. You can figure that out. At home, can you guys figure out what the pH would be when it's 50? All right? And then you should be able to figure out, as you add incrementally, you can figure out what the pH of that solution is. All right? Now we're going to look at what happens at the equivalence point. So the third scenario is at the equivalence point, or stoichiometric point. Now this is when they have both neutralized each other. So what you need to know is at the equivalence point, the moles of hydronium ion, okay, should equal the moles of hydroxide. All right? And so remember, we know that C equals N over V, therefore N equals C times V. So the moles of acid that you added would be the concentration of H3O plus times the volume of the acid should equal the concentration of hydroxide times the volume of hydroxide that's added. So you can see that if this is 0.10 moles per liter, and we started with 100 milliliters, let's say, we know that on the other hand, if this is 1 moles per liter, what should this volume come out to be? Can you see that? So that means you know that if you start with 100 milliliters of 0.1 molar HCl, what is the volume of NaOH that you need to add? You have to add 100 milliliters. All right? So this is what you calculate. You have to figure out. So usually, you know that if you want to calculate the volume of hydroxide that needs to be added, that would be the concentration of hydronium ion times the volume of the hydronium ion divided by the concentration of hydroxide. So for a strong acid, strong base, you can actually calculate, if you know the concentration of your analyte, you know the volume of the analyte, you know the concentration of a titrant, you can calculate how much volume you need to add. And we know that when you add 100 milliliters of the base, it's going to be completely neutralized. When it's completely neutralized, what is the pH? pH should equal, because all we have there is just water and salt. And therefore, for strong acids, strong bases, when the pH is 7, we know it's neutralized, and that is the stoichiometric point, or the equivalent point. Now, what happens if we add an excess of base? Okay? So let's say now we have hit the equivalence point. Now we're going to add an excess. So the fourth scenario is pH after 200.05 milliliters of base is added. Is that clear to everybody? All right, so now we've gone beyond the equivalence point, and now we have excess base. All right? So, so what I want to start by asking you is, what is the total volume of that solution when we're at the equivalence point? Remember, we said that the equivalence point you have to add 100 milliliters of base. So what is the total volume at the equivalence point? 200. So we know total volume at equivalence point, I'm writing too fast now. If you can't read what I'm writing, let me know. So total volume at equivalence point would be 200 milliliters. All right? So what is the volume of excess hydroxide? Can everybody see? It'd be 200.05 milliliters minus 200 milliliters, which is 0.05 milliliters. All right, so that's the volume of the excess hydroxide that we figured out. Okay? So now if I want to figure out what the pH of the solution is, I need to figure out how many moles are in that 0.50, because the early amount was consumed and neutralized. So the only extra hydroxide that you have in there is 0.05 milliliters. So what is the moles of that? All right? So remember, moles of excess hydroxide is always, moles is what? Concentration times volume. The concentration of this is 0.10 moles per liter, times the volume now would be 0.05 divided by 1,000 liters. All right, so it's 0.05 milliliters. I have to convert that to liters. And so if you work this out, this comes out to be 5 times 10 to the negative 5 moles. Oh, actually, it's 10 to the negative 6. Sorry. All right? So I've calculated the moles of excess. You can see that I now have, because I'm subtracting these two numbers, I end up with a 1 sig fig number, and I'm carrying it over to 1 sig fig number. Okay? So this is the amount of excess number of moles. So now, because the volume changed, I know I added 0.05 of NaOH. I figured out the moles, but now my total volume is what? 200.05. Do you see that? So that means if I want to calculate the concentration, I figured out the excess hydroxide, the moles, and therefore if I want to calculate the amount concentration of excess hydroxide, this would be 5 times 10 to the negative 6 moles divided by the new volume, which is 200.05 liters. Do you guys get that? I've converted, the total volume is now 200.05 milliliters, converting that to liters, and therefore this comes out to be 10 to the negative 5 molar. Now I want to remind you guys that this is a 1 sig fig number, and therefore this outcome should be 1 sig fig, but what I'm doing is I don't want to artificially inflate this number, so I'm just carrying this 5. If you divide 5 by 2, you end up with 2.5, all right? And so I'm just carrying, this number should strictly be a 1 sig fig number, and I should round it off to 3. But if I carry that number 3 over, you can see that I'm artificially inflating that number. So I'm putting that subscript 5 to remind me that I'm just going to carry this number over, and at the last, I'm just going to round off to 1 sig fig. All right? Yes?
How did you know the equivalence point was 200 milliliters?
Because remember, at the equivalence point, you have 100 milliliters of this, and we had to have 100 milliliters of the other. all right? And at the equivalence point, you're going to have equal moles of acid and base. So that's the calculation that we did here. You see that? At the equivalence point, we calculated that we have to have 100 milliliters of base. So that means you have 200 milliliters of this. So now that I have hydroxide, I can calculate hydronium. We know that's Kw divided by hydroxide, which is 1 times 10 to the negative 14 divided by 2.5 times 10 to the negative 5, which gives me 4.0 times 10 to the negative 10 molar. All right, so again, I'm just carrying this to 2 sig figs. My result should be 1 sig fig. Now if I take the pH of that, that comes out to be 9.4. You guys understand how I calculated the pH? So I calculated the pH corresponding to that little excess of hydroxide that I added beyond the equivalence point. So in this way, you can calculate the pH of any point in the titration. All right? Next class, we're going to look at weak acid, strong base titration. Okay?